back to part 2. So finally we want to show the following. So here's the theorem. We want to show that 1 over 1 plus 1 over 4 plus 1 over 9 plus 1 over 16 plus in general 1 over k squared is equal to pi squared over 6. So this is some finite number. Okay, so proof. So Euler started with some infinite polynomial and he chose the following particular function. So let f of x be the following infinite polynomial: 1 minus x to the 2 over 3 factorial plus x to the 4 over 5 factorial minus x to the 6 over 7 factorial plus x to the 8 over 9 factorial, and so on. So it looks almost like the sine function, but not exactly, because the powers here are not the odd powers. Okay, so this is an infinite polynomial. This is an infinite polynomial. Okay. With f of 0, what is f of 0 here? Meaning, if I substitute x with 0 here, what would I get? I will always get 1 because all those terms vanish. So this particular function or infinite polynomial that Euler chose actually fulfills one of the conditions that we actually mentioned last time, or part 1. So if we could possibly determine the roots of this polynomial, and we know that f of 0 is equal to 1, then we can factor it out the very same way as the finite polynomial that we mentioned in part 1. So if we can determine the roots of f of x, then we can factor it into star. Star is the same polynomial, factorization of the same, not the same, but of some finite polynomial that I mentioned in first part, meaning by star I mean exactly this way of factoring the polynomial. Okay, so you should have that from page 1. Okay, note that for x not 0, for x not being 0, I can multiply and divide the terms at the same time, the terms of this polynomial, by the same quantity, and let me call that x. So for some x not 0, I can multiply and divide every term here by x. So let's see what I get. We have f of x is equal to x times this entire thing, 1 minus x to the 2 over 3 factorial plus x to the 4 over 5 factorial minus x to the 6 over 7 factorial plus x to the 8 over 9 factorial, and so on, the whole thing over x. So I'm taking my original polynomial and I'm multiplying and dividing by x at the same time. So f of x becomes, well, what does it become? It becomes the following. you multiply x with everything on the top, and let's see what we get. X times 1 is x. X to the 2 over 3 factorial times x would be x to the 3 over 3 factorial. This is x to the 5 over 5 factorial minus x to the 6 over x to the 7, what am I saying? X to the 7 over 7 factorial plus x to the 9 over 9 factorial, the whole thing over x. Well, okay, then in this case the top is nothing other than the sine function that we talked about in part 1. So my original function, this one, can also be rewritten as sine of x over x, because this is equal to sine of x from part 1. Alright, so now instead of dealing with this function, I'll deal with the roots of a function that we have a better knowledge of. And we can determine the roots of this, but not so much the roots of this. So that is actually the point. Okay, so as long as x is not 0, solving f of x equals to 0 amounts to solving sine of x over x equals to 0, which is a whole lot easier. Okay, so let's work with this now. So sine of x over x equals to 0. This will be 0 if and only if sine of x actually is 0, because we're demanding that x itself is not 0. So this will be true only if sine of x is actually equal to 0. But from part 1 we know that sine of x is equal to 0 exactly at x equal to 0 plus minus pi plus minus 2 pi plus minus 3 pi and so on. So we are going to eliminate 0 here, because we are only talking about x not equal to 0. So the roots of this polynomial are just plus minus pi plus minus 2 pi plus minus 3 pi and so on. So but we eliminate x equal to 0 as a solution, since we know that f of 0 is actually equal to 1. Okay, so as I said before, the roots therefore would be these. Okay, since the roots are these, then just like in the first part, I can take those roots and I can factor my function or my infinite polynomial whose roots I found into something of this form. I repeat, this is something that can be done for a finite polynomial, and Euler used this pattern to reason that whatever works for a finite polynomial in this case in terms of factoring should work for the finite infinite polynomial as well. So here's what we do. This means that now we can write our original function as the roots are plus minus pi plus minus 2 pi plus minus 3 pi and so on. So I can write my polynomial now as the product of the following things. 1 minus x over minus pi. Again, a, b, c, d are the solutions, and here I'm going to write minus pi, plus pi, minus 2 pi, plus 2 pi, and so on, times 1 minus, well, I can say pi here, minus pi there, doesn't matter. So this is minus pi, this is plus pi, times 1 minus x over 2 pi, times 1 minus x over minus 2 pi, times 1 minus x over 3 pi, times 1 minus x over minus 3 pi, and so on. Okay, so this will be actually equal to, again, 1 minus x over pi, times 1 minus and minus is plus, so x over pi, times 1 minus x over 2 pi, times 1 plus x over 2 pi, 1 minus x 3 pi, times 1 minus or plus x over 3 pi, and so on. Okay. All right, here it is okay to regroup this product as follows. Okay, so now I have things to this form. 1 minus something times 1 plus that same thing. So this is just the product of two conjugates, and we know what that is equal to. So a minus b equals to a plus, not equals, times a plus b. It is equal to a squared minus b squared. So that's a product of two conjugates from your early algebra. So this product here, it is equal to 1 minus x squared over pi squared. This product here is equal to 1 minus x squared over 4 pi squared. And this product here is equal to 1 minus x squared over 9 pi. 9 pi squared, and so on. Okay, so we're saying the following. I'll leave this aside for a minute. I will continue here. So we have what? Let's see. We have the following. We're saying that our f of x here, f of x, is equal to this infinite product. So let's write it. So we mean the following. 1 minus x to the 2 over 3 factorial plus x to the 4 over 5 factorial plus, minus x to the 6 over 7 factorial plus x to the 8 over 9 factorial, and so on, is equal to this infinite product. So let me write it. 1 minus x squared over pi to the 2 times 1 minus x squared times 4 pi to the 2 times 1 minus x to the 2 over 9 pi squared over 2, and so on. Okay, great. So now what? Now Euler imagined actually multiplying out these things infinitely many times. If you remember from part one, we said the following. So we said the following from part one. if I have three things that look like 1 minus ax squared times 1 minus bx squared times 1 minus cx squared, and if I had more of those, if I was to multiply them out, I should be getting something that looks like this. 1 minus x squared times a plus b plus c plus x to the 4 times ac plus bc plus ab minus abcx to the 6 and so on. So if you notice in the right hand side, you do have something of that same form. You have 1 here, you have an x squared and an x squared here, and your a here is 1 over pi to the 2. Your b would be 1 over 4 pi to the 2, and your c would be 1 over 9 pi over 2. So if this is true for some finite product, then it should be true, if you were to multiply this out, it should be true that you should get something like this as well. So here isn't that 1 minus x squared over 3 factorial plus x to the 4 over 5 factorial minus x to the 6, 7 factorial plus x to the 8, 9 factorial dot 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 must equal to something that looks like this. 1 minus x squared. Your a is 1 over pi squared, 1 over pi squared. Your b is 1 over 4 pi squared, and your c is 1 over 9 pi squared. Then you'd say plus x to the 4 times something else minus x to the 6 times something else, and it doesn't matter for the moment what this something else is. The bottom line is that if I was to multiply these things out, just like in the finite case, the coefficient of x to the 2, it would look something like a plus b plus c, or in our case 1 over pi squared, 1 over 4 pi squared plus 1 over 9 pi squared. So, and that's all he needed to actually complete this proof. So how do we complete this proof? Well, we're saying the following. We have a polynomial that has, so we have established that these two sides are equal to one another. These two infinite polynomials are equal to one another. So if these two infinite polynomials are equal to one another, then the coefficient of their respective powers should also be the same. So coefficient in front of x squared here is minus 1 over 3 factorial, whereas coefficient in front of x squared here is exactly this number. Well, I made a mistake. I shouldn't say just these three numbers here. You have infinitely many of those sums. It's not just these numbers, so I should point that out. This sum here would be an infinite sum because you will have infinitely many such x to the 2's being multiplied out or being distributed eventually. I wrote only 3 by mistake because 3 was the case that we discussed first, but it's not just 3 here, it's infinitely many. Okay, the same here. You'll have infinitely many terms that are being added, infinitely many terms here that are being added, and so on. But the bottom line is that the term x to the 2 will have a coefficient that looks like this infinite sum. So on the right hand side, the coefficient of x to the 2 is this number minus this infinite sum, and the coefficient in front of x to the 2 here is minus 1 over 3 factorial. So if I have two infinite polynomials that are equal to one another, so we have established already that these two sides are equal to one another, then you can freely equate coefficients. So you can equate coefficients of x to the 4 with this. You can equate minus 1 over 7 factorial with whatever this infinite sum will be for x to the 6 on the right hand side, and so on. So this implies, very important here, I have an infinite sum, I repeat. So this implies that minus 1 over 3 factorial must be equal to the same coefficient of the term x squared on this other side. So it must be equal to this other sum, 1 over pi squared plus 1 over 4 pi squared plus 1 over 9 pi squared, and so on. Okay, here, well, the minus and minus cancel. Then 1 over 3 factorial is the same as 1 over 6. Here, if you notice, 1 over pi squared is a common factor of all of these terms, so I can factor that out, or I can bring that in front, and I'll be left here with 1 plus 1 over 4 plus 1 over 9, and so on. Okay, wait, but this is exactly the sum that we're investigating. So this means that the sum that we're investigating, 1 plus 1 over 4 plus 1 over 9 plus plus plus, is equal to, it is equal to 1 over pi squared divided by 1 over 6, and that is the same as saying pi squared over 6, which was to be proved. Okay, so we will get back to part 1 to multiplying out 3 factors in a little bit, but this is something that you can investigate on your own. I can just point out what is that you should look for. But meanwhile, let me just make some comments about some further series of Euler. So much for this particular sum. Now, if you look back at the function f of x equal to sine of x here, so looking back at f of x equals to sine of x over x, we said that this function is equal to this formula, is equal to 1 minus x squared over pi squared times 1 minus x squared over 4 pi squared times 1 minus x squared over 9 pi squared, and so on. Okay, now Euler considered what happens if you substitute in this formula x for x with pi over 2. X with pi over 2. So what would be f of pi over 2 as far as this function is concerned? Okay, so f of pi over 2 would be the same as sine of pi over 2 over pi over 2. And if you substitute x with pi over 2 here, let's see what we have. We shall have 1 minus pi over 2 squared, so pi over 2 squared over pi over 2 times 1 minus pi over 2 squared over 4 pi over 2 times 1 minus pi over 2 squared over 9 pi over 2, and so on. Let me work this out a little bit. So sine of pi over 2 is actually 1. So 1 over pi over 2 is the same as 2 over pi. Sine of pi over 2. Sine of pi over 2 is 1. So 1 over pi over 2 is 2 over pi. So we're saying that this is equal to, well, you will have here pi over 2 over 4 over pi over 2. So pi over 2 will cancel with pi over 2. and you will be left with 1 minus 1 over 4 times 1 minus 16. Jesus. This other one would be 1 minus 1 over 36. And if you were to continue, the next term would be 1 minus 1 over 64, and so on. Okay, so what is the big deal? So this will imply that 2 over pi is equal to 3 over 4 times 15 over 16 times, if you were to do the math inside, 35 over 36 times 63 over 64, and so on. Now, if you are to take the reciprocal of that, you'll have pi over 2 equals to 4 times 16 times 36 times 64 times over 3 times 15 times 35 times 63 times whatever. But this is the same as writing 4 is the same as 2 times 2, 16 is the same as 4 times 4, 36 is the same as 6 times 6, 64 is the same as 8 times 8, and so on, over 1 times 1 times 3, 3 times 3 times 5, 15 is 3 times 5, 35 is 5 times 7, 63 is 7 times 9, and so on. So if you notice, this is nothing other than saying pi over 2 is actually equal to 2 squared times 4 squared times 6 squared times 8 squared times, continue taking the square of all even numbers, over the square of odd numbers. So 3 squared times 5 squared times 7 squared times 9 squared, and so on. So what is the big deal? Well, there is no big deal other than another formula for another explicit formula for computing or approximating pi over 2. This formula was actually known before Euler, but proved differently. It was known by Wallis, and again, it is a completely different proof. So a few more comments about Euler series, or this particular series, and what he did with it. So let me continue. Still with part 2. Just want to mark my margins. Bear with me for a moment. Okay, so this was another formula for pi over 2. Now, Euler realized that the technique that he developed in the previous sum was actually the key to evaluating other type of series. For example, the next series he considered was the series of the form 1 over 4 plus 1 over 16 plus 1 over 36 plus 1 over 64 plus 1 over 100. As you can see, this is nothing other than the infinite sum of the reciprocals of even perfect squares. 2k is another notation for even numbers, and power 2 is what we call perfect squares. So this is the next thing that he considered. Now, with the result that he already had before, he realized the following. In this kind of sum, you could do what? You can first factor out 1 over 4, as it is a common factor in all terms, in infinitely many of those, and then you'll be left with, the first term will be 1, the second term will be 1 over 4, the third term will be 1 over 9, the next term would be 1 over 16, 1 over 25, and whatnot. So, but this is the sum that previously he proved that it was equal to pi over 6, pi squared over 6. So this other new series now can easily be evaluated simply by using the previous result, pi over 2, pi to the 2 times 6, and this is pi squared over 24. Or the next one, he considered actually the perfect squares of odd numbers. So what are those? 1 over 1 plus 1 over 9 plus 1 over 25 plus 1 over 49, and so on. So 2k minus 1 or 2k plus 1 squared, 1 over 2k plus 1 squared. Okay, well, here with this sum, let's see what can be done. So you can break this sum as follows, actually. So you can consider 1 plus 1 over 4 plus 1 over 9 plus 1 over 16 plus 1 over 25, and so on, minus 1 over 4, 1 over 16, which is the one that we know from before. So this would be the one that we know from before, and this will be this one, minus 1 over 4 plus 1 over 16 plus 1 over 36, and so on. We just proved from the previous step that so part 1, this is equal to pi squared over 6. This part is minus pi squared over 24, and the final answer to that is pi to the 2 over 8. Okay, so he continued showing also the following. Well, I'm not giving a proof here, but I'll tell you how he proceeded with the proof, and maybe you can see if you can figure this out yourself. It's also given in the book too, so it's definitely worth reading. So he went on to actually show the infinite sum of the reciprocals of the fourth powers, and this was a little bit more difficult. It was not as obvious as the previous three. So next he proved 1 over 16 plus 1 over 81 plus 1 over 250 plus 1 over k to the 4. He showed that actually this is equal to pi over 4 over 90. Now, and he went on to prove the 6th powers, the 7th powers, up to the 26 powers, the reciprocals of the 26, power 26 of positive integers, the infinite sums, that is. So 1 plus 1 over 64 plus 1 over 729 plus 1 over 4090 plus 1 over k to the 6 plus so on. He proved that this is actually equal to pi over 6 over 945, and he went on until 1 over k to 26, and this is where he actually stopped. Now, about this, let me get back to part 1. And I will copy what I wrote once again about these sums. I'll rewrite this again. So 1 minus ax squared times 1 minus bx squared times 1 minus cx squared, we said is equal to this one, is equal to 1 minus x squared a plus b plus c plus x to the 4 times ac plus bc plus ab minus abc times x to the 6. Okay, so we already have shown, meaning we made use of the fact that when you factor out something like this, the term x to the 4 has this kind of coefficient. Okay, so in order to prove the infinite sum of the reciprocals of the fourth powers, the idea is exactly the same just as in the proof of the very first one, except that now Euler had to instead of equating powers, coefficients of terms x to the 2, he was going to equate the coefficients of term x to the 4. And in this case, the coefficient of the term x to the 4 would look something like this. So here's what we do. Keep in mind the following. AC plus BC plus AB, not that this is obvious in any way, but certainly is true algebraically speaking, it is the same as the following quantity. So if you do the algebra, you see that this is right. Half times A plus B plus C squared minus A squared plus B squared plus C squared. Well, let's see if this is actually true. Okay, so A plus B plus C squared is the same as A plus B, if you want to consider that as a group in its own, plus C squared, or equals to A plus B squared plus 2A plus B times C plus C squared, or A squared plus 2AB plus B squared plus 2AC plus 2BC plus C squared, or it is equal to A squared plus B squared plus C squared plus 2 times AB plus AC plus BC. Okay, so this entire thing therefore would be equal to what? Would be equal to half. Instead of A plus B plus C squared, I'm going to write whatever that is equal to. So A squared plus B squared plus C squared minus 2 AB plus AC plus BC minus A squared minus B squared minus C squared. Okay, this is plus, I'm sorry. Okay, so this and this cancel, this and this cancel, this and this cancel. You are left with half times 2 times AB plus AC plus BC, which is exactly the same as this. So this is equal to now AB plus AC plus BC. So the key is to rewrite something like this as something like this, and then equate the coefficients. That's exactly what happened in this proof. You just have to do some bookkeeping with the algebra when it comes to equating the coefficients, but otherwise is not a difficult proof. So with that, I'll stop, and I'll assign some homework from the PDF that probably deals with one of those proofs, see if you can figure this out, and maybe something else from the very same section. So until next time, everyone, so long.